Hi, it is section 4.3, monotonic functions and the first derivative test. This section is part of curve sketching. In the next section, we'll consider more systematically about curve sketching. In this section, we'll study basic mathematical principles for that. Let's begin with another consequence of the mean value theorem. F is continuous on a closed interval, a and b, and differentiable if f prime is positive at each point, then f is increasing on the interval. If f prime is negative at every point, then f is decreasing. This corollary can be easily proved by using mean value theorem. Okay, here. And between A and B, now that is closed interval A and B, we are choosing arbitrary 2 points here now, x1 and x2, with x2 is right side of x1. Choose such 2 points. Then for this point, and there must be point C between x1 and x2 such that now f of x2 minus f of x1 and divided by x2 minus x1 is same as f prime at C. That is the mean value theorem. Now the denominator is multiplied to become here now right hand side factor. Then we can see this equation. Here x2 minus x1 is positive, and so that f prime at C is positive, and for every value is positive. Then now here, and f of x2 minus f of x1 is positive, which means that and right side, x2 is the right side of x1, right side, the value is larger, which means that f is increasing. The other way, f prime at C is negative, then here f of x1 is larger. That means the left side is larger and going down, which means f is decreasing. So from the mean value theorem, we can prove this corollary quite easily. A function that is increasing or decreasing on an interval is said that it is monotonic on the interval. So here definition is monotonic on the interval. So over the whole interval, it may not be monotonic, but if you choose subintervals part by part, you can find the monotonic behavior. So by choosing subintervals, and you can say it's monotonic over the subinterval. Okay. In this example, we'll try to find the critical points of the function, and we try to identify on open intervals, and so that f is increasing or decreasing. Okay. Okay, let's try to find the critical points. It is differentiable, so that the critical points are the point where f prime equals 0. Okay, f prime, that's 3x squared and minus 12. Now that is 0. Then it's the same as x squared minus 4 equals 0. So x is now plus minus 2. These are critical points. Okay, so that here now minus 2 and 2 at the point, the f prime is 0, and now you can find the signs of f prime, and here and this subinterval, that is now from -2 up to -infinity, left side, and that is between -2 and 2, and that is from 2 to infinity. So you can find the sign. Right now, f prime is given in this way, which means that if you are making f prime, then it is given in this way. It's go down and go up. That is 2, and that is a -2. Of course, there is y called f prime, not f. Okay, here, f prime is positive in that side, so that it is positive. And between -2 and 2, f prime is negative. Now, here, in larger than 2, then f prime is positive. We already know from the corollary that f prime is positive, then it's increasing. F prime is negative, then it is decreasing on the interval. So even though it is an infinite interval, now here f is positive means that it is increasing. Now if f prime is negative, then here it is decreasing. Now f prime is positive, then it is increasing. Okay. You can do that. Here now, value of f, so to make a sketch, if we can see the value of f, then you can do it in a much better way. Here at -2, so let's try to evaluate the f value here. At -2, that is -8, now plus 24, and -5, so that is 11. Okay. Now when at x equal 2, that is now 8, -12, -5, that is now -9. So here, the values of f here, that is now 11, that is -9. And of course, at x equals 0, the value is -5. So you can make a sketch roughly in this way. That is x-axis. Now that is y-axis. Okay. Now here at -2 and 2, the slope must be 0, so that it is horizontal around there. Now at 0, it's passing -5. At here, -2, the value is 11. So that is now 11. At 2, the value is now -9. So that, okay, we say here now that is -9. So looks like here coming up and is horizontally changing and go down passing this intercept. And then here we have passing this one and start coming up like that. That is rough sketch. And through the derivative, we can see the behavior of f. And here, left of -2 is increasing. Between -2 and 2, it is decreasing. And so that in each subinterval, it is monotonic. And also, if x is larger than 2, then again, it is increasing. So in this way, we can understand the behavior of a function. And if you can sketch the function graph very nicely, then you can do it much better and much more in your applications. So that's the purpose of this section and the next section. Okay, here we have a first derivative test for local extrema. Okay, suppose C is a critical point. So around the critical point, we try to use the first derivative to understand that the critical point is either maximum or minimum. And and C is critical point, but around there, F is differentiable. So this differentiability is around the C, possibly here except at C, and around there is differentiable. Like in this case, at the point, if you choose this as C, then at point C, because it's cursor, it is a critical point. However, at the point, it is not differentiable, but around there, left-hand side, right side, the derivative, you can find the derivative. And here it is positive, the derivative is negative. You can see that. But at the point, the derivative is not defined. So yes, that test is saying that once C is critical point, then possibly except at C itself, F is differentiable around there. Okay, around there. Then moving across the interval from left to right, we can say this. Once F prime changes from negative to positive, which means that negative means the F is go down, and now positive means F is coming up. So that at the critical point, F has a local minimum. Quite clear to see that, right? And as in this picture, right now is negative, F prime is now negative, and F prime is positive, so that at the point, the critical point is a local minimum. And also F prime changes from positive to negative, like in this case, it's positive to negative or positive to negative, then it is a local maximum. If F prime does not change the sign at the point, it can be critical point, but sometimes it's not changing the sign. Like this one, is go down and again go down, so that here F prime is negative and it becomes 0 at a moment, and then now it is again negative. F prime is negative, so this point is not extremum. Okay, so that here is not a local extremum. So we can decide by using the first derivatives, and by checking the sign change, you can say there's a local maximum and local minimum. Okay, let's go back to the earlier problem. Right now, yes, this point and that points are critical points, and the sign of F prime is positive and becomes a negative, so coming up and down, so that at the point it is a local maximum. Here, as you can see in the figure, is a local maximum. And now the sign of F is negative and change it to become positive. So this go down and up, so that at the point it should have local minimum. Okay, that's the first derivative test. Okay. F is given in this way, x squared minus 3 times e to the x. Okay, let's try to sketch and let's try to identify local and absolute extrema. Okay, by solving ABC step by step. Part A, first we have to find critical points. To do that, F prime, so that is now here 2x and e to the x plus, by using product rule, we are differentiating the function, and that is x squared minus 3 and e to the x, so that is same as x squared plus 2x minus 3 and e to the x. We can make this one x-axis separation and 1 and 3 separation. Here plus 3 minus 1. So that now that is here x minus 1 and x plus 3 and e to the x. Okay. So once we try to find the critical point, we equalize this term 0. Then, and e to the x is always positive, so that only the possibilities comes from this one, so that now x is 1 and minus 3. There are two critical points. And here we want to identify and open intervals on which f is increasing and or decreasing. Okay, here f prime is given in this way, and now this is positive, and if you are considering only this portion or that portion, then here the shape is basically, now that is minus 3 and that is 1, and the quadratic part gives in this way, so that here f prime in this side must be positive, and between minus 3 and 1 there must be negative, and larger than 1 is positive. Okay, so let's try to make a table as in the previous example here. Now, okay, we are making table. That is now x value. X is here minus 3 and 1. Then f prime, the sign of f prime is we have here, that is 0, that is 0. Now that side is positive, and between minus 3 and 1 that is negative, and once x is larger than 1 it is again positive. We checked here, and so we did here for second part, so that the interval minus infinity to minus 3 is now f is increasing, it's monotonic, and between minus 3 and 1 f is decreasing, so that we can say again behavior f, that is now increasing and now decreasing and again increasing, like that. You can make such a table in this way. So find the function's local and absolute extreme values. Okay, so here we evaluate at f and minus 3 and f at 1, then you can find the extreme values. Let's try to get it by using octave. Okay, what is the function? Function is x squared minus 3 times e to the x. Okay, let's try to implement the function. Okay, that is f is now function of x, and that is here x squared minus 3 times exponential function of x. Okay, so f of minus 3 and f of 1. So one is about 0.3, one is about minus 5.4. Okay, so here, and that value, okay, I'll move the, okay, f of minus 3 is about 0.3. It's about 0.3, and now f at 1 is about minus 5.4. Okay, we found that. So here, and we can sketch that now, and here once okay, x is larger than square root of 3 or less than minus square root of 3, then that value is positive. And with the multiplication is e to the x. Now e to the x will go to 0 much faster when x becomes smaller, so then approaching minus infinity, then this value is the reducing 0 much faster than that one, so that later we'll study that. But anyway, here we have, we can sketch in this way. Okay, that is minus 3, that is 1, and at minus 3 the value is about 0.3, and at 1 the value is minus 5.4. And once x is approaching minus infinity, but anyway, that side is decreasing so that it is becoming 0. Now here, from minus 3 to 1, it is decreasing, so it go down. And now, after 1, it is start increasing. Now it will become infinity later on. It's increasing this way. So that is a rough sketch of the function. And of course, over there, that minimum is about minus 50.4, and that local maximum is about 0.3. So yeah, that is local maximum, and this is absolute, of course, local and simultaneously absolute minimum. That there's no other point having less than this value, because this side is always positive, so that is now absolute minimum. Okay, this is a rough sketch from the table anyway. Okay, that is end of section. Thank you.